in philosophy in 1999 at Leeds University. His area of specialty are philosophy of science, philosophy of mathematics, philosophy of logic, philosophical logic, epistemology, metaphysics, philosophy of art, areas of competence, logic. Currently, he's a professor and a chair of the Department of Philosophy at the University of Miami. Also, he's the Cooper Senior Scholar in Arts and Science at the University of Miami. He's currently the editor-in-chief of Census and the Census Library book series. He's the co-author and the co-editor of several books, including Applying Mathematics, Immersion, Inference, and Interpretation, co-authored with Professor Stephen French, published in Oxford University Press. Okay, you can see this several his books. He has published over 200 articles in journals and collections. His work appeared in journals such as News, Mind, British Journal of the Philosophy of Science, Philosophical Studies, Philosophy of Science, Census, Journal of Philosophical Logic, Studies in History and Philosophy of Science, Analysis, Study in History of Philosophy of Modern Physics, Alchemist, Monist, Metaphysics, Philosophy, and so on. You see many very good journals. Also has given over 600 talks worldwide. In 2022, he has been elected as a full member of International Academy of the Philosophy of Science, AIPS. Okay. He will deliver two online lectures on modal epistemology, invited by School of Philosophy at Wuhan University. Last Thursday night at Beijing time, he gave the first lecture titled Modal and Modal Knowledge. And tonight at Beijing time, he will give the second lecture titled Necessity and Contingency, Quantum Mechanics, and Empiricist Modalism. Now the time is for Professor Otávio Bueno. Please and welcome. Okay, tonight we have the interlocutor, Dr. Fan Da from the School of Philosophy at Wuhan University, and currently he's a postdoctor working with Professor Chen Bo. Okay, Professor Otávio Bueno, now it's your time for your lecture, please.
Okay, so first of all, thank you so much, Professor Yong Cheng, for the lovely introduction. Also, I'd like to thank again for the invitation from Professor Chen Bo to give these lectures. It's been a pleasure. It's always wonderful to be able to speak to my Chinese colleagues. So tonight, I'm going to develop further some of the themes I've started in my previous lecture, emphasizing the role that modality plays in a concrete case of a particular scientific theory, right? So in the previous lecture, I discussed why the sort of modality is not a features of the models that we use to represent the world, but it's better thought of some features of the objects in the world itself. I'm going to develop this theme further within the scope of a particular empiricist view, which I call Empiricist Modalism, for reasons that will become clear later in the lecture, and considering specifically what an empiricist modalist has to say about the role of modality in quantum mechanics, given the significance of quantum physics to our understanding of the world. Okay, so let's start. So So first, there's no question that modality plays a significant role in quantum mechanics, right? For example, it's invoked in the impossibility of certain quantum configurations, right? In the necessity of certain radioactive decays, or the probability, which can be thought of as a modality with degrees of certain experimental outcomes. So modality is it's crucial throughout the sciences, and not surprisingly, will be crucial specifically in quantum mechanics. So the question I'd like to address is, what is the source of this modality? Right? Bob Hale asks this kind of question in the context of logic and metaphysics. I'm going to try to ask that question in the context of quantum mechanics. Right? If certain quantum events are necessary, or if they are possible, in virtue of what are they necessary and are they possible, right? In particular, should the necessities involved in quantum mechanics be explained by other necessities, or can they be explained by contingencies, right? Which of the two is more basic, right? The necessities or the contingencies, right? Those are fundamentally different ways of thinking about how to account for modality, right? So there are those approach, this so-called necessity first approach. They take necessity as basic, right, and use necessity to explain the contingency. So they start with what's necessary and try, in terms of what's necessary, explain the deviation, right, the contingent. The contingency first approach do the reverse. They say, look, the world is a world of contingent events. What requires explanation are events that are necessary. Those are the unusual. Those are the deviation from the norm. So in this paper, what I'm going to do is to identify two roles of modality in quantum mechanics, one involved in the characterization of the quantum domain, and another regarding the specification of the states of a quantum system, right, and what it can be. So there are many roles, right, but I'm going to identify these two roles as being central. And one is central to what quantum mechanics is, what characterizes the domain of the theory. And another is central role of modality to specify the states of a quantum system. And once characterized, these two roles are then going to offer an empiricist modalist approach that insists that the source of modality is found in the relevant properties of the objects under consideration, right? While resisting several attempts to account for that source of modality that rely on conventions, on models, or on essences. And so overall, as will become clear, what we're going to do ultimately is offer a defense of a contingency first approach, which should not be surprising given the empiricist leanings of the view that I'm going to favor, right? The world of empiricism is a world of contingencies, not a world of necessities. Right? So, and I'm going to contrast this alternative with other attempts to answer the question about the source of modality that rely on conventionalism, that rely on model theoretic considerations, and on essences. And I'm going to indicate there are problems with each of these alternatives and offer an empiricist view as a way of making better sense of the phenomenon. Okay, so let's start with the two roles of modality in quantum mechanics. The first one is the way in which the characterization of quantum mechanics ultimately relies on the modal character of the objects under study. So let's consider what Dirac has to say, right, in his Principles of Quantum Mechanics, so a classic book that sort of orient and structure the field. He notes in the book that quantum mechanics may be defined as the application of equations of motion to atomic particles. On the surface, this may seem to be an entirely non-modal way of characterizing quantum mechanics, right? There's no modality, right, in the statement there. It's just a matter of applying equations of motion to quantum particles. But the question is, how exactly should those particles, these atomic particles, be understood? And as I'm going to indicate, it's in the proper understanding of the particles that the modality, the modal content of the characterization of quantum mechanics will emerge. So here Dirac offers an account of what atomic particles are in terms of relational properties of the particle's absolute size, thus bypassing altogether the thorny issue of the constitution of such particles. So it's very clever what he does. And as I'll become clear in a moment. And so he realized that if you start talking about the constitution of these particles, you end up maybe going into a regress. So he tries to block that by just saying, look, there is a general way of characterizing the particle's absolute size. And in terms of that, specify the domain of the quantum. So first he contrasts classical and quantum explanations, right? He says, in a classical explanation of the constitution of matter, one would assume it to be made up, so matter is made up of a large number of small constituent parts, and one would postulate laws for the behavior of these parts, from which the laws of the matter in bulk could be deduced. So just a familiar way of saying, okay, look, we have large number of small constituent parts, and then there are laws regulating the behavior of those parts. So that's what we find in classical mechanics. He continued, this would not complete the explanation, however, since the question of the structure and stability of the constituent parts is left untouched. So, of course, you need to then say, okay, what about those constituent parts? To go into this question, he says, it becomes necessary to postulate that each constituent part is itself made up of smaller parts, in terms of which its behavior is to be explained. So he realized that, okay, we need now to say something about the constituent part of those smaller parts. But here he thinks there is a limitation. There is clearly no end to this procedure, so that one can never arrive at the ultimate structure of matter on these lines. So he realized we are up to infinite regress if we just keep dividing up and up into smaller parts. So long as big and small are merely relative concepts, it's no help to explain the big in terms of the small. It's therefore necessary to modify classical ideas in such a way as to give an absolute meaning to size. So see what Dirac realizes. If we are to characterize what quantum mechanics is in terms that are not relative, we need some absolute notion of what's big and what's small, so that we avoid this infinite regress, right? Not because we stumble into the basic building blocks, right? But because we identify what's big and small, and the theory will presumably deal with the small in a way that can be determined without an infinite regress. So we need some non-relative notion of small, right, to do that. So in the end, an absolute characterization of size is required to specify the nature of atomic particles. And in order to do that, Dirac considers the nature of observation and the fact that it requires an interaction between the object observed and some external influence. So he says, okay, let's try to understand what exactly those particles are. He says, at this stage, it becomes important to remember that science is concerned only with observable things, and that we can observe an object only by letting it interact with some outside influence. I think this is an interesting statement. It's actually an empiricist statement, right? Science is concerned with the observable, right? And the observation requires some kind of interaction with an outside influence. An act of observation is thus necessarily accompanied by some disturbance of the object observed. We may define an object to be big when the disturbance accompanied by our observation of it may be neglected, and small when the disturbance cannot be neglected. This definition is in close agreement with the common meanings of big and small. So what he realizes is, look, understand by big, now he's trying to characterize what a big object is relative to our observations of it, right? So an object is big when the disturbance that accompanies our observation can be neglected, right? So any observation will disturb the object. But if the object is big, that disturbance doesn't make any difference, right? Or can be neglected. But if an object is small, any disturbance cannot be neglected. Noted also already here the emergence of modal language here, right? It's a disturbance that cannot be neglected. So you can already see how slowly modality is creeping in the characterization of the objects. And Dirac says, it's usually assumed that by being careful, we may cut down the disturbance accompanying our observation to any desired extent. The concepts of big and small are then purely relative and refer to the gentleness of our means of observation, as well as the object being described. So this is the way that it's usually assumed, right? In order, however, to give an absolute meaning to size, remember, that's what Dirac needs in order to have his proposal work, right? We need to avoid the infinite regress, you need an absolute size, an absolute meaning of size. So in order to do that, such as required for any theory of the ultimate structure of matter, such as quantum mechanics, we have to assume that there is a limit to the finiteness of our powers of observation and the smallness of the accompanying disturbance, a limit which is inherent in the nature of things and can never be surpassed by improved technique or increased skill on the part of the observer, right? So note what Dirac is realizing here, that there are some limits, right? To avoid that infinite regress, we need to realize that there are limits to how fine our observations can be, right? And this is because of the nature of things, right? It's not about us, it's about the way the things are. So it doesn't matter that we may improve our techniques, that will not change, right? These limits, right? So it's the nature of things that determines whether objects are small or not. Smallness is not an instrument-dependent property that results from our interaction with increasingly more powerful tools of observation. So Dirac is saying, look, there's something about the objects that we're trying to understand, right? They require that they are small in and of themselves. So he continues, if the object under observation is such that the unavoidable limiting disturbance is negligible, then the object is big in the absolute sense, and we apply classical mechanics to it. If, on the other hand, the limiting disturbance is not negligible, then the object is small in the absolute sense, and we require a new theory for dealing with it, namely quantum mechanics. So he's here finally specifying what is the domain of the quantum, right? The quantum is characterizing contrast with the classical theory, right? Classical theory is here understood as a domain in which objects are so big that the unavoidable limiting disturbance, the disturbance of any observation, is negligible. However, this is not the case for quantum mechanical objects, right? The limiting disturbance there is not negligible because the objects are small in this absolute sense. So now we can return to Dirac's original characterization. And remember, he tells us that quantum mechanics may be defined as the application of equations of motion to atomic particles. Right? And we can now combine this with his account of the nature of atomic particles that we just found. And then we get this. Quantum mechanics is the application of equations of motion to small objects. That is, to objects that by their very nature necessarily will be disturbed when under observation in a way that cannot be neglected. The modal content of the characterization of quantum mechanics is now salient, right? Once we spell out Dirac's understanding of what atomic particles are, they're small in this absolute sense, we realize that the very characterization of the nature of quantum mechanics requires modality, right? Because it's a study of objects that are by their very nature necessarily will be disturbed under observation, and that disturbance cannot be neglected. So note that Dirac deliberately articulates an account of quantum particles in terms of small objects that has a decidedly deflationary understanding of object. Right? There's no specification here about the ultimate size, right, other than being small. And that's important because we just don't know what this ultimate size is. Right? So we're studying it. Their nature, constitution, and divisibility, right, including any commitment to atomism, is not to be found here. Dirac is deliberately silent about any of that, right? He's deliberately silent about any sort of metaphysical commitments about the nature of these objects. The only thing needs to specify is that the quantum objects are small in absolute terms. That is, that they necessarily will be disturbed under observation in a way that cannot be neglected. In this way, Dirac very ingeniously and carefully bypasses any philosophical difficulties that a more robust notion of object would have brought, right? Because these more robust conceptions will bring in a lot of metaphysical worries that he sort of bypass by saying we don't need to settle any of those things if we have this modal understanding of quantum objects. And this deflationary account of objects, as will become clear, meshes very well with an empiricist modalist, right, view, which says exactly that we don't need to have any sort of extra metaphysical description about the nature of quantum objects to understand what they are. But we do need some basic modality in that characterization. That's exactly what Dirac did. So it's an interesting example of a sort of an empiricist view at work. Okay, so this is one important role of modality in quantum mechanics, to characterize the very domain of the quantum as the study of the small. A second role of modality is in order to specify the states a quantum system can be in. Suppose that we have any indistinguishable quantum particles, right? For example, you may have any electrons. According to the theory, it doesn't matter which electron you're considering, they're indistinguishable from one another. They have, they satisfy the same properties, and it doesn't matter which one. There's no individuality of an electron. As Weil said, there's no alibi for an electron, right? You cannot say, hey, this is Ike, this is Mike, and this is the one who did it, right? So because you just swap them around and the quantum system remains the same. Right? So consider then, among those indistinguishable particles, and the interchange or any pair of such particles. So you're just permuting them one for the other. And I have something quite interesting. If the particles are totally symmetrical under the interchange of any pair, they are bosons and satisfy the Bose-Einstein statistics. If the particles are totally antisymmetrical, they are fermions and satisfy the Fermi-Dirac statistics, right? So again, those are features of the particles at hand, right? Depending on, and those features will specify the kind of statistics that they satisfy. Now, Sakura, in his very good presentation of quantum theory, tells us an immediate consequence of the electron being a fermion is that the electron must satisfy the Pauli exclusion principle, which states that no two electrons can occupy the same state. This follows because a state like this one is necessarily symmetrical, which is not possible for a fermion. And so note right here the modal content of this description, right? Which states are possible is determined by the quantum objects under consideration. And this in turn determines the relations these objects can or cannot enter, depends on whether they are bosons or whether they are fermions. Right? So the very characterization of the states and the states that the systems can be in is a modal characterization. Right? It's in terms of what if the state is necessarily symmetrical, and it's not possible for a fermion to be in it, right? Because the fermion will require these antisymmetrical states. So, interestingly, we find here in the very characterization that is of a system, a quantum system, a modality, a crucial modality built in. Sakurai continues, we see that in the fermion case, it's impossible for both particles to occupy the same state. In the boson case, for 2 out of 3 allowed cats, both particles occupy the same state. That's why they have the statistics that they do. In the classical Maxwell-Boltzmann statistic case, both particles occupy the same state for 2 out of the 4 allowed cats. So here, basically, what he's referring to is if you have 2 particles, right, in 2 states, in classical mechanics, right, you have 4 possibilities, right? The 2 particles are in the same state. The 2 particles are in the other same state. One particle is one state, the other is in the other state, or vice versa, right? So 4 possibilities, each of them have the same probability, right? That's why you can have both particles occupying the same state for 2 out of the 4 allowed states. Now, in quantum mechanics, since the particles lack individuality, when you may have both of them in the same state, both of them in the other state, but then when you have one in one state, one in the other, and vice versa, the vice versa determines exactly the same state. So there are only 3 possibilities, right? Because we're unable to distinguish the particles, so we're unable to distinguish the states in which these particles are in. And hence, instead of having 1/4, we have 1/3 as the probabilities, because there are only 3 possible states. Note again the modal content of this formulation. The possibility of occupying certain states or not is determined by the relevant quantum objects. Right? So again, it's the modality here that is central to formulating what the possible states are or are not. So, given these 2 roles of modality, right, in characterizing the very domain of the modal, in characterizing the states of a quantum system, what exactly is then the source of modality in quantum mechanics? There are 4 possible answers here that I'm going to be considering, right? First, a conventionalist answer, right? The source of modality is found in linguistic conventions, right? That's a famous, important philosophical view about the nature and source of modality. Second, a model theoretic approach. The source of modality is found in the models of the theory. Third, an essentialist view. The source of modality is found in the relevant essences, right? Because objects have some essences, and those essences then determine what's necessary or possible for the objects. And finally, the empiricist modalist view that I favor, the source of modality is found in the relevant objects. They have modal properties, And it's because of these modal properties, the primitive modal properties, that the objects have the modal features that they do. So let me consider each of these. As will become clear, I think there are problems with the first three alternatives, the conventionalist, the modal theoretic, and the essentialist view, and I'm going to favor an empiricist approach instead. Okay, first, conventionalism. And I said that it's the source of modalities found in linguistic conventions. Now, why is it necessary that a bachelor be unmarried? Right? Well, the conventionalists, because bachelor means unmarried male. And hence we have that unmarried male is unmarried, right? Just follows logically from that. And so from the sort of conventions of linguistic use that we have, follows analytically. But I think this approach is inadequate, since it needs to assume the necessity of unmarried male is unmarried in order to conclude the necessity in question, right? And arguably, the necessity of this statement is not a matter of convention, right, but a logical truth, right, assuming classical logic. And so you're basically, because if you note, there is no explicit modal statement here, right? We just say, well, bachelor means a married male. But from this, it followed that an unmarried male is unmarried by substitution of terms. But where is the modal content of these convention, right? So the necessity of unmarried male is unmarried has then to be assumed rather than accounted for. And ultimately, it's the necessity of the statement in question is not a matter of convention, but it's a matter of the logical truth. And that one has to be the necessity of that logical truth that needs to be accounted for, right? Presumably, it's not a matter of convention. If it is also a matter of convention, then again, we're just back to the problem. What is the source of the modality in the first place? Now, it's similarly unclear how the modalities involved in quantum mechanics would be a matter of convention, right? Recall Dirac's formulation, and we saw that he notes that quantum mechanics is the application of equations of motion to small objects, that is, to objects that by their very nature necessarily will be disturbed when under observation in a way that cannot be neglected, right? Recall that formulation. Now, it's not a matter of conventions about the meaning of small that yields the necessities in question, but rather the necessities are the result of the properties of the relevant objects, right? It's because the particles are small in the sense that they will be disturbed in ways that cannot be neglected when observed, that they are small. It's not a matter of the way we use the term or the conventions that we adopt for regulating the vocabulary as small. So what it seems that the conventionalist is missing here is the objectivity of the modality in question. It's not a matter of just having conventions, of regulating the use, but it's a matter of respecting the modal properties of the objects in question. So the objects are small, and thus necessarily they will be disturbed when they are observed in a way that cannot be neglected, right? So it's because the objects are the way that they are that they will behave in the way they do. The modality seems here to come from the objects rather than from any linguistic convention about them. So it's hard to reconcile this feature with a purely conventionalist treatment of modality. Okay. Recall again Sakurai's observation, right? We saw, you notice that an immediate consequence of the electron being a fermion is that the electron must satisfy Pauli's exclusion principle, which states that no two electrons can occupy the same state. This follows because a state like this one is necessarily symmetrical, which is not possible for a fermion, right? So note that it's not the case that electrons satisfy Pauli's exclusion principle due to a matter of linguistic convention. right? This principle describes features of electrons rather than linguistic usage. It's difficult to see how a conventionalist can actually make sense of the fact that when quantum physicists are describing features of electrons, they're not describing features of our use of the vocabulary about a modal vocabulary or a vocabulary about what's necessarily symmetrical. They are describing features of the electrons, right, the objects, rather than our terms to describe them. So rather, the satisfaction of Pauli's exclusion principle results from the necessary symmetry of the relevant state, which rule out fermions, right? So it's the fact that we're dealing with necessarily symmetric states that we're going to rule out fermions, right? And then the Pauli's exclusion principle is satisfied. There are other forms of conventionalists, however, right? But it's not clear that they fare better. So, for example, some conventionalists will insist that the truth of axioms, including of those axioms invoked in mathematical physics, is a result of a conventional decision of taking them to be basic principles, and thus to be constitutive of certain domain of inquiry. No analyticity is involved in this process, right? So perhaps the conventionalists may say, yeah, look, what we need here is just that a realization that there is a conventional element in the choice of what are the axioms, including axioms in mathematical physics, that are adopted as basic principles, right? And then they constitute the domain of inquiry. Now, the problem with this conception is that it fails to take the objectivity of necessity seriously. Because what is necessary is so independently of us. As we saw, if fermions cannot be in certain states, this is so given the properties of fermions, rather than the result of adoption of certain principles, even constitutive ones about them, right? So it's not because, hey, we adopt these principles about fermion, therefore that's the way they are, right? It's the other way around. Fermions aren't the way that they are, and maybe that's why certain principles were adopted. But that means that the adoption of those principles about fermions is not a matter of a conventional decision, right? It's actually a matter of describing properly the behavior of the fermions in question. So it's ultimately a matter of the relevant properties of fermions, rather than of one's decision about principles that allegedly describe their behavior. Result, this proposal ultimately fails to explain the source of modality. In virtue of what are necessary statements necessary, right? After all, taking something to be necessary or true does not make it true or necessary, right? Because if the proposal is, well, look, there are certain principles that are the basic principles that are constitutive of these description of these objects, that doesn't make it necessary that the objects have those principles, because then what is the source of the necessity of the principles themselves, right? And that's exactly, as I noted earlier, what the conventionalist is unable to account for. Now, other conventionalists maybe will take basic principles to be such that the principles hold come what may, right? They are true under every condition. So say, hey, so let's have those basic principles, but they are necessary because they hold in any condition, right? So come what may. I think this is an improvement and a step in the right direction toward taking necessity's objectivity seriously, right? Because now you say, okay, there's something about the objects in question that will make it hold no matter what. But note that this is no longer a form of conventionalism, since the necessity of the relevant situations is not a matter of convention anymore, but the result of certain features of the objects in question, expressed by the generality of the truth describing them, or by their independence from particular domains, right? So it's the fact that he holds no matter what, or holds come what may. This generality is a fact that it doesn't matter, right? the specific features that are adopted, once they're fixed, they'll hold no matter what, because the objects themselves are of that way. So this form of thinking, this is a way of trying to capture a notion of necessity, but it's no longer a form of conventionalism here, right? Because it's the necessity is not the result of a convention. The necessity is a result of picking out a feature that would then be generalized. It can be generalized given the nature of the objects, given what the objects are. As a result, I think a proposal along these lines, rather than a form of conventionalism, will move closer to a form of empiricist modalism that I'll discuss later. But why? Because it's sensitive to the objects at hand rather than to our linguistic conventions, as will become clear in due course. Okay, so those are reasons to be skeptical about the ability that conventionalist views have to explain properly the nature of the source of modality in quantum mechanics and beyond. Let's look now at a second possible answer to the source of modality, right? A model theoretic one. And that one insists that the source of modality is found in the models of the theory. Right? So von Frassen defends such a view. We discussed this aspect of his view in last week's lecture. Right? If it's not possible for an object to be both red and green all over, it's because the model of the color spectrum, which represents the wavelengths of various colors, involves no overlap in the model among the corresponding colors. Right? So von Frassen says, look, there is a modality built into the model. Right? So it's not possible for an object to both be red and green all over, because the model itself is such that there is no overlap between the color spectrum of the wavelengths in question. But this approach seems to get the situation exactly backwards. The color spectrum, understood as the wavelengths associated with the various colors, a physical process in the world, is a physical situation. The lack of overlap among the wavelengths, a physical situation, grounds what the model represents, rather than the other way around. The model character constitutes what the modality is, right? So in a way, the same worry that I raised against the conventionalists a minute ago, it's also involved here, right? So it seems that the problem is in assuming that the modality, the source of the modality, can be having the way in which the modality is itself represented, as though it's just a feature of the model in this case, rather than a feature that the model represents because the world has those features in itself. Similarly, in the case of the quantum, being small rather than big, as characterized by Dirac, is not a matter of the models used in quantum mechanics. Rather, as we saw, these are properties of quantum particles that characterize what they are. We saw that Dirac, in an empiricist way, made exactly that move. Right? He said, look, these are ways in which these particles are. And because when they are observed, we cannot ignore or make negligible the influence that observation has on that. Also, if electrons must satisfy the Pauli exclusion principle, this is a fact about electrons, properly conveyed in the relevant quantum mechanical models, but not determined by the models themselves. So again, the models encode features of the world, and that's why they accurately model those features, rather than stipulate what those features are. Right? So, third, essentialism. And this is a view that insists that the source of modality is found in the relevant essences. Objects have properties they have, including their modal properties, because of the kind of objects they are. So essentialism, in contrast with both conventionalism and the model theoretic approach, at least move in the right direction of recognizing that objects have properties, and including their modal properties. And this is a move in the right direction, right? So what they try to do then is just say, look, but the objects have these properties because they are objects of a certain kind. And the general essence of an object of a certain kind, K, is what it is to be an object of that kind, K, right? That's how Jonathan Law thinks about essence, right? So the general essence of a certain kind is what is to be an object of that kind. The object's individual essence is what is to be the individual of kind K that object is. So what the essentialist thinks is, look, objects have properties, but to understand why they have these properties, we need to identify their essence. And because it's in virtue of the essence of the object that the object is what it is. What is the object that it is? And so the essence will specify the kinds of properties that the object has. That's the idea. But I think this view approach faces serious difficulties in quantum mechanics. So in quantum mechanics, first, it's unclear whether there are individuals, right? So in some interpretations, at least in one interpretation of quantum theory, identity cannot be applied to quantum particles, right? This is a view that we find in Schrödinger and Weil, right? In their book, Stephen French and Desi Krause on identity in physics, developed an entire approach, taking very seriously in what senses these particles are not individuals, right? I already alluded to in the discussion earlier on Sakurai, when you have like the fact that the particles satisfy the permutation invariance principle, right? So if you have two quantum particles, you swap them around and the states they are in do not change. There's nothing in the quantum mechanical formalism that allows us to individuate, so identify the particles. So this is Ike and this is Mike, right? And these are different electrons, and we swap them around and I can trace where they are. And this is exactly what the theory doesn't allow us to do. So in that sense, the theory, at least on that particular interpretation, makes no room for individuals. Right? And so we cannot, as a result, talk about individual essences, right? Because as you can see, in the way that Lowe understood an individual essence, right? It is to be an individual of a certain kind that requires individuals, right? And that's incompatible with certain interpretations of quantum mechanics, right? So we have here a case where a particular philosophical doctrine is actually incompatible with some understanding of quantum physics. And I think that's a problem for the philosophical doctrine. Now, talk of general essence is similarly problematic. How could it be determined what is to be an electron without relying on a theory, quantum mechanics, that describes perhaps equivocally what is to be such an object? And so there's no way of characterizing what the general essence is of an electron but by relying on quantum mechanics itself, right? Now, then we start having some uncertainties. Is it part of the essence of an electron that it satisfies Pauli's exclusion principle? Right? Or this is just a contingent fact about electrons? How can we determine those things? Right? So, because part of the issue is what makes Lowe's account of essence, sort of an Aristotelian understanding of essence, so attractive is that it's very general, right? An essence of an object is just what it is to be that object. But if I don't know what it is to be that object, that account is woefully uninformative about the essence, because unless I already know what the object is, I don't know its essence, right? But if I already know what the object is, I don't need to talk about its essence anymore, right? I'm just talking about the objects and its properties, and I'm done with it, right? And that's exactly what the trouble we are finding here in the context of quantum mechanics. I already need to figure out whether Pauli's exclusion principle is a contingent or a necessary property of an electron. I already need to have an answer to that question given by the theory about how central it is, that property, right? So arguably, something wouldn't be an electron if it violates the principle, right? So you may say, well, in that case, it looks like it's a necessary property. But if it is, we can make sense of that without talking about essences at all. And we just say, all right, nothing could be an electron unless it satisfied Pauli exclusion principle. And we bypass the need to talk about essences altogether. All we need is just a modality, right? Just in the way that we saw Sakurai characterizing those things. Just a modal characterization of the objects in question is enough. We don't need the detour through essences to reach that. Now, it's unclear here what explanatory work essences ultimately provide. Specifying the kind of thing something is simply moves one level up the description of the relevant object. It does not account for the behavior or the trace of these objects any more than the direct descriptions of the objects already does. So the worry here is, okay, essences and framing things in terms of essences is just sort of a perfectly dispensable way of maneuvering things, because it just invites us to move one level up and talk about kinds of things rather than just talk about the things themselves. So the issue is not a matter of the legitimacy of using certain expressions, right, such as essence or kind, but identifying the explanatory power of a certain style of reasoning. My point here is that it's unclear that an additional form of understanding is offered when it's noted that something behaves in this way because it's an object of a certain kind, right? Because it has a certain essence. Since this seems to add very little to what is already provided by the description of the object in the first place. Right? When I'm describing the object, I'm already describing in terms of the properties that the object has. Otherwise, I'm describing some other object. I don't need to say on top of that, oh, by the way, that description, that's the kind of object that it is. That's its essence. I don't need that extra gloss, philosophical gloss on the description of the object. Empiricists can, of course, use kinds without refining them by noting that they are just plurals of particular objects, right? So you can say, look, when I'm talking about a kind of objects, I'm talking of objects like that and give the properties of the objects. When I'm talking about electrons, I'm talking about things that have negative charge, have a certain mass, have some spins of certain things, and those are what electrons are. I don't need to say, look, this is the essence of the electron. I don't need to reify them as, okay, these are the essential properties of electrons. At least, the empiricists will be very sensitive and careful not to reify things in that way. Now, returning to the quantum mechanics, as we saw, given Pauli's exclusion principle, no two electrons can occupy the same state. Right? This results from the fact that states like this one is necessarily symmetrical, and this is not possible for a Fermi. Right? Note that satisfying the Pauli exclusion principle is a consequence of certain modal facts about electrons and the necessary symmetry of certain states. Rather than essences, it's modality that accounts for the behavior of electrons. And that's the crucial move here. Right? We don't need modality, we don't need essences here once you already have the modal. Right? And that's exactly the way that Sakurai operates. And that's another reason why we do need to understand the role that modality plays in quantum mechanics. But that role does not require an essentialist gloss on that modality. If you have the modality, you have all you need to characterize the objects in question, because their modal properties is what's involved in specifying the objects. Now, perhaps an essential dispositionalism could overcome these difficulties, right? That's a view that Conrad, O'Connell, and Taco developed. According to the essential dispositionalism, they say any electron, X, essentially has the disposition to become modally connected with respect to some property or properties with an electron or electrons Y. So any electron is, has a disposition to be modally connected with other electrons when a certain condition C obtains for such an electron, right? And for an electron to be in that condition is for it to be entangled with other electrons. Okay, so that's the idea of the essentialist dispositionalism, right? An electron is essentially disposed to become connected with other electrons in a certain condition, when this condition is a condition of entanglement. And of course, they are nodding here to the crucial role that entanglement has in formulating quantum phenomena. Note that what's essential to an electron here is not that it's modally connected with any electron or electrons. Rather, what is essential to the electron is that it has a certain disposition to become modally connected. So it's a disposition to become modally connected that is central, right? When this entanglement condition is met. So that's their idea, right? He said, okay, maybe we don't have those direct essences per se, but we have sort of an essential dispositionalism, which is the idea that it's a certain disposition of becoming modally connected that plays the role. That's the idea. Okay, two concerns here. First, the proposal seems to be restricted to a particular kind of interaction, namely when a condition C is satisfied, right? And this condition we saw involves an entanglement of an electron with other electrons. There are, of course, other kinds of interactions, however, in quantum mechanics, such as when an electron is absorbed by a proton in the nucleus of an atom. These interactions will also have modal force, but are not accommodated by dispositional essentialism, because, of course, underlying here the view is that entanglement is what's essential to quantum mechanics. But there's more to quantum mechanics than entanglement. So if that's all we're going to say that is essential, it looks like we're going to miss some of the central features of the phenomena we're trying to make sense of. Secondly, it's unclear what work dispositions are actually doing here. If electrons must satisfy Pauli's exclusion principle, this is not because of their disposition to become modally connected with other electrons. It's because of the necessary symmetry of those states, right? Which is not possible for a fermion to be in, right? So it's, again, similarly to my concern about essences, bringing in disposition seems here unnecessary, provided that we already have some modal discourse, which we do, right, or modal properties, right? So, because ultimately, it's not a matter of electrons having a disposition to become modally connected, right? It's because the necessary symmetry of the states, which are not possible for fermions, that's what makes the state what they are. Again, it's a necessity, a modality that is playing the work, playing the role here. It's not the disposition. So we can, in the end, it's modality rather than disposition that is doing the relevant work. All right. Finally, after seeing the difficulties of these three views about the source of modality, can we do better? And so what I want to do in closing is just consider this empiricist modalism as a better way of understanding the source of modality in quantum mechanics. Objects have properties, including modal properties. The table in my office is breakable, given the material it is made of. That it is breakable is a modal property of the table. So, as you can see, throughout the talk, I was already, emphasizing the role that the modal properties play in quantum mechanics. Right? This is a role that the modal properties play even in ordinary objects, such as the table in my office. Right? These are properties that my table has. Similarly, fermions and bosons also have modal properties, as I have been emphasizing throughout. Right? We saw that it's impossible for fermions to occupy the same state, whereas it's possible in some cases for bosons to do so. These are possibilities or impossibilities of the objects in question. As we also saw, an electron must satisfy Pauli exclusion principle, according to which two electrons cannot occupy the same state. This results from the fact that states like this is necessarily symmetrical, and this is not a possibility for a fermion. Again, these are modal properties of electrons. You need to consider the properties of the objects under consideration, as good empiricists do. Finally, in terms of Dirac's characterization of quantum mechanics as the application of equations of motions to small objects, we saw that small objects are those that by their very nature necessarily will be disturbed when under observation in a way that cannot be neglected. Right? These are modal properties of the quantum objects that quantum mechanics focuses on. So note that throughout here, we have an emphasis on the objects, right, as good empiricists do, right? And an understanding of what the modal properties that these objects have. And it's because they have these modal properties that they behave in the way they do. So obviously here, as will become clear, modality is crucial. Right? I'm taking modality here as central. And also, it's an empiricist view, given that it's the modality is coming from the objects. So we're on the basis of which we have observations. We saw how Dirac was saying, look, it's because of the nature of observation that requires some kind of intervention and some kind of influence in the objects that we need to determine which objects are small and big as properties of the objects. Again, we're following the evidence, right, about what is observable here, right? Now, it's important, of course, we're talking here about properties of electrons and things of that sort, but empiricists, and or no one else for that matter, can actually see, right? So how can we do it? And empiricists can do that. And the point here is, and I think in this sense, Von Frassen is correct, empiricists can do that because all we need here is a theory that is empirically adequate. And quantum mechanics arguably is. So that we follow the theory in describing what electrons are, but we need not be committed to electrons existing, right? That's an extra commitment that will require proper evidence. But if the theory is empirically adequate, what it says about the observable is correct, and that we can have access to. And in that way, it's still a form of empiricism. So according to the modalist empiricism, modality is primitive, right? There is no attempt here to reduce the modal to the non-modal, right? Something that I don't think can be done in any case, right? As I mentioned also in last week's lecture. And any attempt, it's, for example, using possible worlds to try to specify in known modal terms what modality is, will require a notion of, say, a logical space about what's possible. And that the very structure of a logical space, for example, in the context of Lewisian modal realism, the very structure cannot be understood in terms of worlds, right? Because worlds are in it, not outside the logical space. But that means that there is a notion of possibility about what's possible or not that frames the structure of the logical space. Now, that's exactly the kind of primitive modality that is needed. And that's what the modalist empiricist would insist needs to be there. It's the appeal to primitive modality to make this proposal modalist, right? Because we cannot explain this modality in non-modal terms. Note that modal considerations in quantum mechanics come in very naturally, both in the characterization of the quantum mechanical domain and the specification of the states of what quantum systems can be in. Right? We saw that that's exactly what Dirac did, and that's the first part of the talk. We saw how that comes about very naturally. So Bayes, Quine, and Lewis, modality, understood as what's possible or necessary, not what is true in some or in all possible worlds, is all mysterious. Right? It comes very naturally in the way that physicists are there describing what fermions are, or bosons are, and how some states are excluded and cannot hold and others are possible. So modality here is not mysterious. We understand this fairly well. So, but you may then ask, why is this a form of empiricism? Right? Now, the proposal focuses on properties of objects that can be detected via suitable instruments without reifying these properties. And this is important, right? So I'm talking about objects and their properties. Objects that are, at least they can be detected via instruments. And in that way, even though some of these objects cannot be observed directly, like an electron, and the theory in which they're embedded is empirically adequate. So there are features of these systems that can be detected and observed. That's how we test quantum mechanics. And so, and the properties that we are describing here should not be reified, right? We should not think of those properties in terms of universals, in terms of possible worlds, in terms of abstract objects, in the way that I discussed in the last lecture, right? Resist the need to add a philosophical gloss to these properties. Take them in the way that the physicists that we just discussed are taking, right? The quantum system is in a certain state, right? A certain electrons are in certain entangled states, and those are properties of the objects. We don't need to have a metaphysical view of those properties in order to understand them. Properties are not meant to be understood in terms of abstract objects, universals, or possible worlds, right? They are just features of things, breakable tables, negatively charged electrons, necessarily symmetric states. We understand that, understand what these things are. We don't need to say, hey, by the way, breakable table is a table such that in a world detached from our own, it actually breaks, right? Because in doing that, I'm actually reifying what a breakability is, moving away from the table. I'm talking about this table rather than what goes on in some other world. That's a form of reification that makes us lose the object we are trying to understand. Finally, note also that this is a contingency first approach, right? What needs to be explained is the necessary. The contingent being ubiquitous with no explanation. This is a feature of an empiricist view, right? The world, as I mentioned, the world of empiricism is a world of contingencies, and anything can happen, right? And that's why empiricists are skeptical about an idea, for example, of laws of nature, things that happen necessarily no matter what, right? The regularities, they're empirical regularities. And we can talk about necessities, as I've been talking about here, but they are always relative necessities. They're necessities relative to a certain context, right? So relative to specification of the state of a quantum system. Those are not full-blown necessities that will hold no matter what, unrestricted. And empiricists will be skeptical about those things. They say, look, there are regularities, but they can be otherwise. Right? So then contingency, the forces. The empiricists should recognize how the sort of necessities that we get are always contextual, always limited to a particular context. So, and then when you realize that, we realize what features need to be in place so that those necessities will take place, right? So in that sense, this is a contingency first approach rather than the other way around. Okay, to conclude, modality is crucial for quantum mechanics, including the characterization of the quantum domain and the specification of the states the quantum systems can be in, as the RAC very clearly indicated. But the source of modality should not be understood in terms of conventions, models, or essences. As I tried to indicate, any of these three approaches face significant difficulties, especially in the context of quantum mechanics. Rather, modality should be understood in terms of the relevant objects and their properties. Empiricist modalism offers then a deflationary account of modality and its source in the context of quantum mechanics. Of course, far more needs to be said in its support, but I think it's in principle a possible way of accommodating the issue, and hopefully something that we should take seriously. Thank you very much.
Okay, first let's thank the speaker for the inspiring, wonderful lecture. Okay, now is our comment and question time. And for people watching the lecture through the 学术2 platform, if you have questions, feel free to propose your question in the chat box, and the staff will forward your question to us. Okay, now first, it's our pleasure to invite our interlocutor, Dr. Van Dahl from School of Philosophy, to give some maybe comment or questions. Okay, please.
Okay, thank you. And thank you, Professor Bueno, for this great talk. Let me full screen this. Okay, so I wanted to first summarize the talk very briefly and then present my comments. So in this talk, Professor Bueno first presented two roles modality plays in quantum mechanics. The first role is that modality is part of what characterizes the domain or the object of study in quantum mechanics. According to Dirac, quantum mechanics applies mathematical equations to small particles. And here, the smallness is characterized in modal terms. And the second role is that modality specifies the states a quantum system can be in. For example, according to the Pauli's exclusion principle, it's impossible that two electrons occupy the same state. Given the two roles, Professor Bueno then turned to the question about the source of modality, namely where the necessities and the possibilities in quantum mechanics come from. First, three attempts are rejected. So the first one is conventionalism, which holds that modality is explained by conventions, such as our linguistic conventions or conventions that we take certain basic principles to be true or to be necessary. So the main challenge raised by Professor Bueno is that these conventionalist views fail to appreciate the objectivity of modality in quantum mechanics. So when we say that it is necessary that two electrons do not occupy the same state, we are talking about properties of particles rather than our conventions. And the second attempt to be rejected is Van Fraasen's modal theoretic approach. According to the view, the source of modality is properties of scientific models. So as Professor Bueno mentioned today, and also in the talk last week, models can encode information about modal properties of objects, but models themselves are not the source. And the third attempt is essentialism, which holds that modality is explained in terms of essences, either essences of individual objects or kind essences. So here the problem is that if the alleged source is individual essences, it may be difficult to apply this view to quantum mechanics because the existence of individual objects or the identity relation is problematic or controversial in quantum mechanics. On the other hand, if the essentialist is talking about kind essences, it is questionable whether kind essences can contribute more explanatory power in addition to mere properties of objects. So also a specific version of essentialism, which is essential dispositionalism, is rejected. Because first, it doesn't apply to a lot of interactions in quantum mechanics, and also it shares the same problem with about explanatory power with the kind essence approach. So with the three views rejected, then Professor Bueno offers his own account of the source of modality in quantum mechanics, namely the empiricist modalism view. I guess who attended the talk last week have been familiar with this view. The core thesis is the view that the source of modality is found in the properties of objects. And these properties are irreducibly modal. They are modal properties. Also, the view has an empiricist aspect. We can attain modal knowledge by knowing modal properties of objects. And these modal properties are empirically accessible. For example, we can empirically detect the breakability of tables and so on and so forth. So, okay, so much for the summary. I have three comments to make about the talk today. So the first one is about conventionalism. If my understanding is correct, I think Professor Bueno's rejection or objection applies to traditional conventionalism well. So the view, the traditional conventionalism view is basically that necessary truth is just truth by convention, or say P is a necessary truth because P is true by convention, by linguistic convention, or by us conventionally taking it to be true, taking P to be true or to be necessary. I think these views fall prey to the objection raised in the talk. First, modal statements in quantum mechanics are not describing our linguistic conventions. And second, conventionally taking certain basic principles or axioms to be true does not thereby make them true or necessary. Consequently, the view fails to appreciate the objectivity of necessities in quantum mechanics. So what I have in mind now is a different version of conventionalism. So this version is proposed by Ted Sider, according to this view, a logical or mathematical or analytic truth, say P, is a necessary truth because first, P is true, and second, we by convention call logical or mathematical and or analytic truth necessary. So based on this, so according to this view, necessary truths are true in an objective sense. They are true about whatever objects they're talking about. And the convention here is that we call certain truth, say truth in logic and mathematics, necessary. So it doesn't rely on the problematic notion of truth by convention. From here, maybe we can make a further move. Say we can explain necessary truth in quantum mechanics in terms of the convention that we call all truth in fundamental physics necessary. For example, consider the statement small objects will be disturbed under observation. So the question is, why is it a necessary truth? Then according to this view, there are 2 points. It's necessary because first, the statement is true, and second, the statement is a truth in fundamental physics. So according to this view, the truth of P is objective, while its necessity is conventional, or specifically, like non-modal statements in quantum mechanics are objectively true because they are true descriptions of objects, such as small particles. But the necessity is just based on the convention that if a statement is in fundamental physics, we call it necessary. So my hunch is that perhaps we can be satisfied with the objectivity of the truth of quantum mechanic statements. And do we have any reason to embrace objectivity of necessity in addition to the objectivity of truth? So that's basically my first question about conventionalism. So the next one is more about the second attempt that Professor Bueno talked about, that is the model theoretic approach. In particular, the worry is that the arguments, the objections, do not seem to appeal to scientific anti-realists. So Van Frassen's view is that the source of modality is found in models, and Professor Bueno's objection, very roughly, is that modal talks in quantum mechanics are about objects and their properties, not about models. For example, being small is a matter of it's not a matter of the models, but rather these are properties of particles, right? So my worry is that a scientific anti-realist like Van Frassen may reject that, say, Dirac's statements are meant to be true of particles in the world. According to his constructive empiricism, assuming particles are unobservable, that's controversial, but let's go along with Van Frassen. So we assume that they are unobservable. And so these statements in quantum mechanics about the unobservable are supposed to describe an empirically adequate model rather than the world, right? So they are not meant to be descriptions of unobservable objects in the world. So it seems to me that Professor Bueno's argument presupposes that the statements in quantum mechanics are about the world, about objective like particles in the world. In other words, the argument presupposes a scientific realist view or a realist reading of quantum mechanics. So if that's correct, then the concern is that the argument doesn't appeal to the anti-realist? So that's the second question I want to raise here. And the last one is about Professor Bueno's own view, empiricist modalism. So as we know, the modalist part of the view claims that the source of modality is found in irreducibly modal properties of objects. And the empiricist part of the view claims that modal properties of objects can be detected via suitable instruments. So I think my concern here is that empirical evidence might not be like rich enough for knowing necessity. So specifically, in a circumstance where a necessary property is presumably detected, the question is our empirical evidence rich enough to rule out the properties being a merely contingent one? Or let's make it more specific. So let's imagine a scenario in which we supposedly come to know that two electrons necessarily don't occupy the same state, right? And in this scenario, we consider what our empirical evidence should include, right? So maybe they should include some observation via some instruments, perhaps cloud chamber pictures and so on and so forth. I don't have enough background in quantum mechanics, so let's say it that way. Given the empirical evidence, it seems to me that such empirical evidence is probably compatible with that the property in question is just contingent, or in particular, the evidence might not be able to rule out that it is contingent that two electrons do not occupy the same state. Well, I think towards the end of the talk, Professor Bueno has addressed the question a bit. So I think your view is that we can treat necessity talks in quantum mechanics as part of a bigger theory of quantum mechanics. And if the theory is empirically adequate, if it's supported by our empirical evidence, then the modal part is also supported, right? We gain evidence for the whole theory, therefore we gain evidence for the modal statements in the theory. But here I want to add perhaps a follow-up question. So let's imagine that the whole quantum mechanics theory can be, so let's try to remove or replace all the modal statements in quantum mechanics theory with its demodalized version, right? So if we have necessarily two electrons don't occupy the same state, we just replace it with two electrons don't occupy the same state, or maybe we can add a universal quantifier to it. So call it quasi-quantum mechanics. So I think my question now turns to be something like, does our empirical evidence really rule out or does it discriminate between quantum mechanics and quasi-quantum mechanics? Okay, so that's my last question, and I'm looking forward to hearing Professor Bueno's answers. Thank you.
Well, first, thank you so much, Professor Dafan. Those are all terrific questions. Very probing, very appropriate, all of them. So, and your summary of the paper is exemplary, very clear, and very to the point. So let me speak to each of your three concerns. I think, in a way, although they are three, they're all interrelated, because all the concerns, in a certain way, indicates a certain skepticism about the very notion of modality, right? So ultimately, it looks at the question saying, hey, I can see you're an empiricist, you want to do without those metaphysical views. Well, why don't you take the next step and just do without modality, right? Maybe all we need is just the actuality, right? So I find in the three questions and in the additional comment, this sort of running theme, right? In a way, I think you are in a very good position. I think that's what von Frassen himself thought of, right? In fact, he characterizing empiricism as a view that denies that there is real modality in nature, right? So I think your questions are questions say, hey, we need to be real empiricists and do without modality altogether. And I think that's what the way von Frassen was trying to approach the field. So that's why I spent the beginning of the talk some time going over in the quantum mechanical literature itself, the way that Dirac, one of the central figures in the development of quantum mechanics, thought about what quantum mechanics is, what quantum mechanical states are. Because, and the point was, well, we cannot just avoid modal characterizations there. I think the worry is an attempt to say, look, let's clean up the theory of any of these extra modal components amounts to losing the theory, because we will not be able to say what the domain of the theory is if we are unable to specify what the small things are. And as Dirac himself indicated, the small is characterized modally, right? As the objects that by their very nature, any observation will necessarily disturb. Now, given what these objects are, this disturbance is unavoidable. So it's not a matter of just saying, oh, look, we're always going to disturb, right? The point is, it doesn't matter what kind of techniques and instrumental developments we have, the disturbance is unavoidable. So if we just replace the modal content of this statement with a sort of an actualized concrete one, we're going to lose the content, right? Because now it becomes, oh, look, so far the interactions are such that when I measure and I try to observe, I disturb. And it has been that way. But maybe with the development of new technologies, this would change. If that were open, we would open to an infinite regress, which was exactly what Dirac was trying to avoid, because we need to break things into smaller and smaller parts forever, right? And he says, look, we'll never be able to achieve that, because it doesn't matter what the technology is, the objects are small in absolute terms, that there is any intervention will necessarily disturb the system, right? So I don't see how we can capture that content of this of the domain of the quantum without the modality, right? So I think there will be a loss if we just say, look, let's replace this just by straightforward categorical statements rather than the modal ones, because even though I do think that the necessities are always contextual, right? I don't think, so my point is, what I grant von Frassen is there are no absolute necessities, right? Completely unrestricted. All necessities are relative to a context, relative to an assignment, even mathematical necessities, right? I don't think that they are also absolute. So for example, if you say, is it the case that every set can be well ordered, right? So you can get a first, second, third, fourth. The answer is, well, depends. If the axiom of choice holds, yes, every set can be well ordered. If it doesn't, no. So even a claim as basic as whether sets are well ordered or not is relative, right? The necessity only comes once the axiom of choice is in place. If the axiom of choice is in place, then necessarily every set is well ordered, right? Even the set of real numbers that we don't know what the well order is, but there is one, right? According to the axiom. But that means the necessities are relative, they're not absolute. And I want to say the same thing goes in quantum mechanics, right? Given the quantum state, right, it's necessary that any observation will alter the state of the system, no matter what kind of technological story we have, right? So that's why I thought that was important to take that modality seriously, right? It's a feature of the objects we're trying to understand, right? It is a feature of quantum mechanics as the theory has been thought of. So it will be a loss to say, look, let's replace that with some categorical non-modal statement. So that's my general sort of response in terms of the costs of trying to avoid the modality. Now, let me then address, in light of this, each of your very pointed objections. So the first one, it's on my treatment of conventionalism, right? And then you bring in Sider's form of conventionalism. And you say, hey, on this form, both a statement will be conventionalist, right? So it will be sort of a necessary truth. If first it's true, and then secondly, by convention, we call the relevant statements necessary, right? First, I'm not on. You're right. I didn't discuss Sider explicitly, in part because it's not clear to me that it does move the debate in a significant way beyond the traditional forms of conventionalism, right? When I said, look, just saying that something is so doesn't make it so in terms of its necessity, right? And in part because I can say all kinds of things so, including impossible ones, right? We can say all kinds, unless there are constraints given by the objects. Impossible things can turn out possible just if I saying so makes it so, right? And that was a source of a concern there, right? So now then you ask a very interesting question. You say, look, okay, let's grant then that when you're talking about small objects, that they are disturbed by observation. So yeah, that's true. The truth is objective, it's not up to us, but the very necessity is conventional, right? So why do we need, you ask, the objective quantum mechanical necessities in addition to the objectivity of quantum mechanical truth? Again, that's a version of let's do without the modality, right? And I think the issue here is, of course, if we just talk about small objects will be disturbed under observation, it may seem on the surface of it that we may not even need any modality, right? It's just that when you press out, okay, but what's the content of the statement, right? What is it that we are saying? And we say that they are not being disturbed under observation. We're actually saying something more than just they are not going to be disturbed. We're saying that they cannot be not disturbed, right? So you're saying something that no matter what interactions we have with these objects, no matter how the technology is developed, any observation will disturb them given that they are small. So the truth here requires the modality so that the proper content is characterized. Otherwise, we're saying less. Right? Okay. If you say, okay, let's do without the modality. Sure, we can, but then we're not going to say all that needs to be said, right? Because then we're just saying that, well, in each case, each observation that we make, there will be a disturbance. But maybe in the future, we'll find one that doesn't, even though the object is small. That's exactly what Dirac's understanding of quantum mechanics precludes. Say, no, we can't, right? Given the nature of the objects. So that's why I don't think that it's enough just to say, let's just hold on to the truth of the statement, right? And I do think we need the modal content to capture what's at issue here. So that's about the first comment. Now then, you raise a really good point in your second objection, right? And the worry there is in the context of discussions of von Frassen, right? You're quite right. Von Frassen emphasizes that modality is a feature of the models, it's not a feature of the objects. This is part of his empiricism. So I'm talking here about objects and their properties. And you say, well, maybe I'm being then a scientific realist, right? And it's very interesting because I think that's exactly what von Frassen would say. And say, hey, you gave up empiricism, man. Come on, right? What's going on? And that's what I want to resist. I want to say, no, I have not, right? I haven't become a scientific realist, right? Because I'm talking about electrons, I'm talking about quantum states, I'm talking about the modal properties of electrons, right? That why, so the fermions cannot be in such and such states. I'm talking about all of that. I'm talking about all of that within the context of the theory, right? Quantum mechanics that allows me to talk about those things. I haven't said that the theory is true. So in that sense, all I did is I'm following von Frassen. Said, okay, I'm not rewriting the theory. When I talk about electrons, I'm talking about electrons. I'm not talking about some, pattern in a clown chamber, right? That might be a track of an electron. That's not an electron, right? So I'm being guided by the theory. I think that was one of the important features of constructive empiricism. I'm taking the theory literally. And note that the theory literally talks about what cannot hold in certain states. So I'm taking that literally, right, as a feature of the theory. But am I now turning to an empiricist, a realist? No, because I'm not taking the theory to be true, right? The theory describes these objects as having these properties and having these modal properties. And I say, look, for the theory to have the content that it has, I need to take that seriously as well. It's just that von Frassen decided to take seriously some portion of the theory, right? But eliminate the modal parts. And I say, well, the modal parts are already there. And you can talk about when you talk about the empirical adequacy of the theory. So I need not assume that electrons exist when I say that electrons are negatively charged and necessarily cannot, necessarily satisfy Pauli's exclusion principle, right? Any more than when I say Sherlock Holmes necessarily cannot fly over the Atlantic. That's true, right? Given the story of Sherlock Holmes, it's a man, and humans are unable to do that. So the object doesn't exist, right? But I'm saying truthfully that, it has certain modal properties. It's unable to fly over the Atlantic, even though it doesn't exist. Same thing goes over electrons. I don't know whether electrons exist or not. But the point is, they do have those modal properties. So that's the idea. I haven't, gone into scientific realism. I think this is still, in a way, a form of empiricism. Now, finally, because I know that Professor Chenbo has a question, just briefly, the last very good question also that you ask about my own sort of empiricist modalism, right? So you ask, how can we have empirical evidence, right, for the necessity of some properties, right? How can we have that kind of evidence? And as you noted, I think in part here, the evidence is given, together with the evidence for the empirical adequacy of the theory, right? Because these modal properties are properties of the objects, right? So if the objects exist, they will have those properties. We may not know that the objects exist, but that will be enough, at least for us to be guided by the theory to describe these objects, right? At least the theory would constrain them as having these modal properties. Now, it may turn out that the theory is false, right? Then okay. Still, I think we would have gotten some understanding about how things could be given if the theory were true, right? And then I think that modal understanding is significant, right? It's within the scope of empiricism. But thank you so much for all the excellent question and pushing me in this way. I very appreciate.
Thank you for all the answers. I know I have taken too much of your time, so I just want to open the floor to the audience. Thank you again for the talk and all the answers.
Yes, I ask a small question. When you talk about essentialism, you said there's no individual in quantum mechanics. When you talk about your empiricist modalism, you said modality is rooted in the property of quantum objects. My question is this: I'm wondering, what's the difference between individual and object? That's my question. Okay.
Great. Thank you so much, Professor Chinbo. This is a great question. There is, I want to say that some objects need not be individuals, right? For something to be an individual, it requires that minimally that we are able to re-identify that individual in various contexts, right? So for example, I'm seeing you now through Zoom. Hopefully in the near future, I'll be able to return to Wuhan, and then I can see you in person and recognize, yes, that's Professor Chenbo, right? I can, because I recognize, your properties, the visually salient properties. So you are an individual, right? Whereas suppose I have a drop of water, right, in a glass, right? And there's one drop, another drop. Is that the same drop, right? The drop of water is an object, but there's no way you can say that it's an individual, right? That I can re-identify. Oh, that's the same drop that I had earlier, right? And that's exactly the problem that we have in quantum mechanics. So we have an electron, right, that the theory describes as, okay, these are objects that have a negative charge, they have a certain mass, they interact with other electrons in this way. But if I swap electrons around, I don't change the state in which they are in. So I cannot say, hey, this is electron Ike, this is electron Mike. And I'm just following them around because there is nothing in the electron that it individuates one particular electron, right? At least according to this interpretation. So they are objects, but they're not individuals because we cannot re-identify them. Hey, this is the same electron here that was there last week. We can do that with people because they have salient properties that individuate them and allow us to recognize them. Electrons don't, right? All I can say is this is an electron. Well, this is also an electron, right? But I cannot say this is the same electron as this one that was here last week. So that's the idea.
Yeah, thank you.
Sure.
Okay.
Okay, please.
Hello? Okay, nice to meet you. It's wonderful talk. So mostly I agree with your view, but I have two questions. Number one is you use the Dirac's view version of quantum mechanics, but the view is 17 years ago. But now the quantum mechanics have a very big development. I see 1930s, the physicists they can get just one electron in the experiment. So they get you use the one electrons do experiment now. But when you agreement you are agree okay, you use the two level model in quantum mechanics. This I agree with you. The one is the general, is from the equation, the Schrödinger equation, and the one is you use the Pauli 不相容原理怎么说的？我已经忘了。
explosion principle.
Yeah.
Okay. So this is right. But my question is, now the physicists can use the one electron.
Okay.
Can I
answer that question?
You want it? Pardon?
So, may I ask?
Otávio, I introduced this is the Professor Chen Shoumei. He he's an expert of philosophy of quantum mechanics. He do a lot research about mechanics.
No.
Quantum mechanics. Okay. Yeah.
Well,
I want to say your view is the empiricism, right? But I want to say that you use the principle is Pauling principle, but it is not experience. It is a principle. It's a theory. It's dependent the theory. So I want to say you standpoint is not really empiricism. It is realism.
Wonderful. Thank you so much, Professor Sumei. Both those are excellent questions. So let me say something about each, right? So you're exactly right. There's a lot of very interesting, particularly on the experimental side of quantum mechanics, a lot of interesting new work that, of course, Dirac had no idea about, right? You have those experiments where you can trap a single positron in a little trap, right? And then, of course, people have said, oh, look, if I have trapped a single positron, I know the identity. Now it's an individual. It's just only one there, right? So now consider the following thought experiment, right? So you have the little trap there, right? And then the professor has a visitor and points out, hey, here's the trapped electron. Isn't it nice? You know, you have now this little, and they even gave a name to it called Melissa, right? And say, hey, this is the trapped electron. So then the professor goes out with the visitor and tells to the postdoc, oh, no, you watch out, make sure that the trap is working properly. We're going to go to lunch and we'll come back in an hour, right? So the postdoc, so they leave the lab, and the postdoc accidentally shut down the whole thing, right? Right? It's, oh my God, what I have to do now? But the postdoc is very able, right? She goes there, reassemble the entire experiment. And by the time the professor and the visitor comes back, there you go. It's the little, positron is there. Can we say that that's the same positron that it was there an hour ago? There's no way of telling, right? So there's no way you can recognize the individuality of that electron. So it's very interesting because even with those more recent experiments, it's not clear that they establish that electrons have individuality, right? And all you have done is, you trapped a single positron in the cage, but that doesn't mean that you have the individuality of it, because you're unable to track it, right? Once the experiment is disassembled. And I think that shows the difficulty, according to quantum mechanics, of actually having that kind of identity.
No, I mean is there are differences between the classical theory and the quantum mechanics about for the 经验 experience and theory. This is different. In the classical theory, we can separate experience with the theory, but in quantum mechanics, there are normally they cannot separate.
Right.
So you cannot separate a micro object and from the theory. For example, do you know the effect of photoelectricity? Do you know this experiment?
Mm-hmm.
Yeah.
Right.
This experiment, the Einstein firstly gave a name of what is photos.
Mhm.
And there you use the photos and explain the phenomena of the experiment, the phenomena. And there we get the fact. This fact is effect of photoelectricity. So they are together. We cannot separate experiment and the theory and use the explaining the some phenomena. So that means, your view maybe realism, not really experience. This is my view. Okay.
Good. Yeah, but the form of empiricism I have in mind here is one that acknowledges that our observations are theory-related. I fully agree with you. There's no way I can describe those quantum mechanical experiments without invoking quantum mechanics, because that's all I have in order to describe, okay, this is a photon, right? This is an interference pattern that I observe in the experiment. These are electrons or positrons. So I need quantum mechanics to do that. But in describing them, I'm not as certain that the theory is true. That's the difference, right? The realist will say the theory has to be true or approximately true. Otherwise, how come he gets all these right predictions? The empiricist says, wait a minute. The theory can get the right predictions if it's empirically adequate. If what it says about the observable is correct, the theory will get the right predictions, even though maybe the theory, what it says about the unobservable, is wrong. And we have many cases in physics where false theories get right conclusions. Right? Newtonian physics is an example. It's a false theory. There's no gravity in the way that Newtonian physics describes, but the theory, we can send rockets to the moon using the theory. You can make predictions about new planets, as happened in the past with Neptune, but the theory is false, right? So I'm being an empiricist in the sense that I don't need to take the theory, quantum mechanics, to be true in order to use it to describe the phenomena that cannot be described in any other way but by quantum mechanics, right? Again, make an analogy with fiction. We have Sherlock Holmes stories, right? And I say, hey, Sherlock Holmes was a great detective. He solves crime brilliantly. He had a friend, Watson. He lived in London, in fact, in Baker Street. All of those things are true of Sherlock Holmes, given the Conan Doyle stories about him, even though Sherlock Holmes didn't exist. Right? I can't say true things about things that don't exist, right? So I don't know whether quantum mechanics is true in every detail. Probably it's not, right? But I can describe properly all the results of those experiments if the theory is empirically adequate. That's the idea of constructive empiricism, right? And it's in that sense that I don't need to be, a realist while describing the phenomena. That's the idea, at least.
Okay, thank you very much.
Thank you.
Okay, thank you. I have two small questions I would like to communicate with you. You claim that the source of the modality is found in a relevant object. So for the term modality, do you mean that it covers all kinds of modality? For example, modality in mathematical and logic, modality in science, especially QM, and modality in metaphysics. So it seems that there are a difference between these different kind of modality. Even we understand this claim in terms of modality in QM. So for QM, it's a question that what is object? What is object in QM? Is there a difference between observed object and unobserved objects? So this is my first question. The second small question is about your claim that modality is primitive. So in what sense that modality is primitive and the model statement cannot be reduced to non-model. For example, if we claim that this statement a state of fields is possible, we replace this statement to the following statement. It's just say that this state of fields happens in some time at some place. So do you think this can be viewed as an example that model statement can be reduced to some non-model statement? Yeah.
Perfect. Thank you so much for both questions. They're very appropriate and very telling. So, I think there is modality. The modality in metaphysics, in mathematics, in physics. The underlying modality is basically the same. What will happen is there are different features of the objects that will be in place, right? So, for example, in the case of physical modality, right? When I mention properties of electrons, and so that electrons cannot behave in certain way, right? That's a feature given the properties of the electrons, right? And the modality there is the same in the sense that certain things go together, certain things do not, right? So we get some contradictions if you were to assume that you could get electrons behaving in some ways, otherwise you couldn't, right? In mathematics, you have something similar in the sense that I do think that mathematics also has modal content, right? So, for example, when I prove that the circle cannot be squared, what I've done is I'm shown the impossibility of trying to square the circle. Any attempt of doing that leads to a contradiction. Now, this is a result given the concepts of circle, square, right? And given their corresponding geometrical properties. So what I would do is, when I establish the impossibility of squaring the circle, is I'm establishing that there is a contradiction in the attempt of doing that, right? In that sense, it's similar, right, to the impossibility in physics. The difference is here, it's a purely conceptual matter, right? In mathematics, all that's needed are the concepts. Of course, if the concept of circle and square were different, well, then the result would be different, right? In physics, it's not a matter of the concept. It's a matter of the properties of the objects as they exemplified in the world. And that's an important difference, because the modal properties of objects in the world have some causal effect, right? There's some interactions with the objects that constrain what can or cannot be done with them. In mathematics, that's not the case, right? And the same thing can be said about in metaphysics. I think that in metaphysics, in a way, it'd be closer to mathematics in the sense that it's a conceptual matter, right? Given the concept of a person that we have, certain things will be true of persons, right? Of course, a different characterization will then lead to different results. But as opposed to mathematics, of course, we want that our metaphysical concepts somehow connect with things in the world, right? So we do have an understanding of persons that would rule out if you say, look, my iPhone is a person, right? Because it has some features that the persons have. And so, well, sorry, there's something wrong here. Right? iPhones and other kinds of things that can be persons. So there are constraints to the appropriate nature of the concepts in metaphysics that we don't find in mathematics. Mathematics, you just introduce whatever you want, right? And then see what follows from that. So the metaphysics is something in between, in a way, between the physics case and the mathematics case, right? So I think there are ways in which you can acknowledge the differences. but they all have something in common, right? Impossibilities will involve some kind of contradiction in at some point, right? And that's a way in which you express those impossibilities. Now, then there's your second question about the primitive modality, right? And the reason why I do think that modality is primitive is because attempts to define modality in non-modal terms end up presupposing the very modality that they're trying to define. And so, and that's a mark of the primitiveness of modality, right? So I gave the example of David Lewis, right? When he says, look, what's possible is what's true in a world, and worlds are just like our own world, maximally extended spatial-temporal regions. These are completely categorical non-modal things. So thereby I have now reduced the possible to the non-modal. Right? That's the idea of reductive, right? The problem is, Lewis says, to every way the world could be, there is a world, there is that way. Right? So then I ask, okay, how about what is it about worlds that precludes the possibility that there is something that is both, say, blue and not blue at the same time? What is it about worlds that excludes impossibilities? If we say, no, it wouldn't be a possible world if you had an inconsistency. Say, wait a minute. Then there is something about the understanding of world that is modal in nature, right? There is something about worlds that need to rule out those contradictions. That's a primitive modality in the background. So the very structure of logical space seems to have some notion of the modal that is not spelled out in terms of worlds, right? So that the world themselves can do their job, right? No world has an inconsistency in it. Otherwise, it would be impossible. So that's just an example, right? It's an argument that Scott Tsiolkovsky makes a long time ago, indicating why modality is indeed primitive, right? You need, even Lewis, at the end of the day, needs a notion of possibility in the background. So the modalist says, okay, so why bother trying to reduce modality? Just take it as primitive and work from there. Even those who try to reduce it cannot do without. So let's just assume what cannot be reduced and go from there.
Okay, thank you. Wonderful replies. Also, thank you for your wonderful lectures. In fact, we have run out of the time. That's the end of today's lecture. Okay, let's thank you again for the speaker, Professor Bueno's wonderful lecture at Wuhan University. Also, we thank all the interlocutor for their comment and questions. Also, we thank the organizer, School of Philosophy at Wuhan University. Also, thank the technical support from the 学术志 platform. Okay, maybe it's time to say goodbye. Okay, and thank you for all of your attendance. Okay, bye-bye.
Otávio, let's look forward to meet together at Wuhan University. Okay.
Very much looking forward to that.
Yeah, in near future, when the COVID-19 crisis is really over, then I can invite you to come to Wuhan University. Okay?
I'll be delighted.
Yeah, okay.
So thank you all.
Very good job. Very good to talks. Okay. I like
Thank you so much. And thank you all for the questions and the comments, and Professor Dauphin and everyone for the engagement and the really helpful feedback. I really appreciate. Thank you.
Okay. Thank you.